for us. And I think for those of you who are tuning in from all over the place, thanks for joining us. My name's David Alexander. I'm the director of the Space Institute at Rice University. And we have this regular series of talks, normally in person. We usually even provide food. So hopefully you've got your own food and drink with you. And it was really, we had to cancel our last talk as things were starting to heat up in terms of closing down campus and so on. And then because there was, it was a real shame to lose that talk. But we already had tonight's speaker, Dr. Kirsten Siebach, had agreed to give one of our talks. And we thought, it'd be a shame to lose both. And we didn't have time to adjust for the previous one, but we did have time to adjust for this one. And so I'm really grateful to Kirsten for stepping up and being willing to do this. And I want to thank everybody for I want you to be patient with us. This is the first time we've done this kind of format, which means that we won't have the ability to do the usual to and fro, but well, hopefully it'll be work. And we are, I hope, recording it. And so it will be available through the Rice Space Institute website, which is rsi.rice.edu. So again, and if you're interested in these talks, we do typically stream them. And we do record them and make them available. You just need to get on our mailing list, which is only purely for talks. We don't try and sell you hand sanitizer or anything. And with that, that's a nice segue to say, I hope you're all healthy. I hope you're all safe. And I hope you're all following government guidelines and doing all the things you need to do to stay healthy and safe. So keep that up and we'll be out of this before we know it. The last thing before I introduce Kirsten is our next scheduled event is a little bit of flux, but it's going to be in September. And it's basically a kind of more of a celebratory event for the 20th anniversary of the Rice Space Institute. We're still working on the actual date because things are changing, because a lot of other things have had to be canceled with this current situation. And so we'll be announcing that, but it will be in September when we're back, hopefully in class. And on campus. So with that, the other thing is the format for this evening is because of the security issues, we switched to this webinar format. What that means is that it's very difficult to have, you can't stick your, well, you could stick your hand up, but I would rather, what we're going to do is leave the Q&A till the end. So we'll let Dr. Siebach give her talk. And then at the end, we'll have a question and answer session. And if you look down, I think on your screen, you'll see a Q&A box. So you can type in your question there at any time. And then at the end of the session, I will read out, maybe not all of the questions, but I'll read out, it's going to be hard to make sure we don't have doubling up and so on, but I will read out questions to Kirsten. And if you add your name, at least I can call out who's asking the question. If I just see your ID number, that's not going to help us too much. So please be patient. If you have a question on the fly, just type it in and it'll be up near the top of the list and we'll work it that way. So I hope that works for us. We'll see how it goes. And so with that, I would like to introduce our speaker. This is a great series of lectures. We've had some great speakers. And the only reason it's taken us so long to get Dr. Siebach tonight is because every time I thought about inviting her, she was already off giving some other talk to some other group. So she's highly in demand for these public lectures. And we're really grateful to have her tonight, even if it's in this kind of strange format. She's been at Rice for 2 years. It's a kind of branching out for what used to be our Earth Science Department. Is now Earth, Environmental and Planetary Sciences. And you can see from her background that there's more than one planet that the Earth Science Department is interested in. And so we're going to hear a lot about that tonight. And particularly interesting is Kirsten has worked with a number of the rover missions, obviously the current one with the Curiosity, and also looking ahead to the next set of rovers. And we might hear about that tonight. I don't want to put words in her mouth, but she's very involved in that whole Martian geology aspects. She does field work here on the Earth to sort of understand more about what we're learning about from Mars by comparing it to the Earth, and a whole range of other interesting backgrounds. She has a PhD in geology from Caltech, and so she's stepping up in the world, coming to Rice. I think we're in for a treat. I've heard Kirsten speak a couple of times, and I'm really looking forward myself to tonight. So I think you might be able to, maybe we don't have reactions, but we'll assume everyone's clapping as I introduce tonight's speaker, Dr. Kirsten Siebach. Thank you, Kirsten, it's all yours.
All right, thanks, David. Let me get this screen share set up. Give me, let's see. All right. All right, so now if you can see my slides, I am excited to be able to talk to you guys today. I haven't spoken to this many people quite this close to my face, so this is a new experience, but it's fun to get to meet up with so many different people. And what I really want to do is kind of go through some stories of the Mars rover and talk about kind of what it's like driving it, what it's been doing in isolation on Mars for the last 7.5 years, kind of some of our key discoveries, and give you a few stories to go home with. So we'll just get started. All right, so humans have been thinking about Mars for thousands of years. So the ancient Egyptians had actually mapped out Mars and tracked Mars movements through the night sky. We've been curious about this neighboring planet for as long as we could see it. And one of our first real maps of Mars, though, came much later. So in 1877, we had our first map of the surface of Mars, and that was by an Italian astronomer named Schiaparelli. And here I'm showing his map. He looked through a telescope that was finally high resolution enough to see Mars and kind of map out some major features on the surface. And you'll see in his map that the northern hemisphere is darker and the southern hemisphere is lighter. And kind of in between, there are a lot of straight, kind of crisscrossing lines. And he was Italian, he called those channels, and in Italian that's canali. And as soon as he published this map, it got over to England. And in England, they were in what was kind of their canal digging phase. They were digging canals in between major cities in order to transport goods more effectively. And so they're in this phase of digging these huge canals so that they can move goods by boat. And they see this map of Mars where Schiaparelli has labeled these as canali, and they were just shocked, right? This was a very advanced civilization because they had figured out how to transport goods efficiently all across the entire planet. And so from then, for kind of over 100 years, we pictured Mars as this place with an advanced civilization. And this kind of led to all sorts of science fiction stories and War of the Worlds and these ideas that Mars was this really exciting place. Now, that led to some disappointment when we got our first real images of the surface in the 1960s. And in the 1970s, when we had actually mapped out the entire surface of Mars in color, we'd gotten satellites orbiting around Mars, the Viking satellites, we could see that, in fact, most of the surface is dry and barren. There is very little atmosphere on Mars, only about 0.6% of the density of the atmosphere that we have on Earth. Most of the surface is ancient and cratered, kind of more like the moon than like Earth. Now, there is ice at the 2 poles. There are white polar caps. And when we look closely at these images, we can start to see that there actually is evidence that Mars was different in the past. Now, this may have been in the ancient past, but it looks like there was water flowing across the surface. And we see evidence for that in these channels where a lot of the surface has been eroded and carried downstream. And you can see these kind of streamlined islands behind craters as these streams kind of covered actually large swaths of the planet. And even in some smaller areas, we have all different scales of rivers that were crossing Mars. sometime in the ancient past. And so once we'd mapped out these, some of this took a little bit of the higher resolution imagery. So it took a little bit of time after the 1970s to see some of these channels. But we started to think maybe we could get some story of what was happening on Mars back when water was active on the surface. But we were worried that we wouldn't be able to get that story because the reason we can read the rock record on Earth is largely because of plate tectonics. So what happens is you've got upstream area, you've got mountains that get built up, and rivers and ice and water and wind erode the sediment and carry it downstream, and it collects in a basin. And eventually that basin, it gets buried and buried and buried, it becomes rock. And then later, at some other point, the continents have moved around in a different way, and that rock is uplifted and becomes a mountain. And then as that erodes, we get to see all of these layers. So when we think of places like the Grand Canyon, we think of all of these layers that we can see. But those have been moved around because the plates on Earth are moving around. And Mars never had plate tectonics. So there were volcanoes and there were rivers, but we were worried that we wouldn't be able to find any place where we could actually see the layers that made up that told us that story of the history of Mars, the history of environments on the surface, until around the year 2000. And one of the key places we looked was this kind of series of craters. And this was an area where we know there were these big floods. There were big rivers that came through here. So there was a big river that carried water into this large crater, which is called Holden Crater. And it actually was so much water that it flooded right out of the crater, right up just out of the screen, and came over here. And there's a little river, you can actually see part of the river channel right where my cursor is. And it came into what was an ancient crater right on the edge of Holden Crater. Now it formed another lake right here. This is called Eberswalde Crater. It formed another lake in this crater. And we're going to zoom in on this white box. So what we're seeing in this white box is where the river that was carrying all this sediment came and entered into a lake. Now, when a river enters a lake, the river has a lot of momentum and it's carrying all this dirt and pebbles and sand with it. And as it's carrying all that, when it hits the lake, there's just standing water and it doesn't have momentum anymore. And so it can't carry as much stuff. And so right where the river enters the lake is where it will end up depositing a lot of its large grained sand and gravel. And this shows us we can actually see where the river entered the lake and it kind of swirled around. These are some of the loops as the river entered the lake and it deposited all of that material. The exciting thing about this is that actually in this case, the rivers look like they're standing tall. This is a cliff where the river has made a deposit that has then everything else has been eroded, and now the river deposit is standing high. What we realized is that the wind on Mars has actually been so strong and had such a long time to erode the surface, probably about 3 to 3.5 billion years of the wind blowing across the surface, that even though we don't get plate tectonics moving things around, the wind can actually erode to show us what the deposits look like. And if we send a rover to see these kind of deposits, we can climb up through different layers of sediment that were deposited at different times. And for each of those layers of sediment, we can look at the rocks and start to tell the story of where they came from and the environment that actually allowed them to be deposited. And I'll tell you some more of those stories in a minute, but this was just a key discovery. So this was the first time we realized we had sedimentary rocks on Mars. And that meant we can go to places on Mars to tell the story of the past. How long ago are we thinking that was? Well, we used different parts of Mars with different amounts of craters to count how many craters have impacted the surface and figure out how old they are. And we compare those crater counts to the moon. And most of Mars' surface is between 3 and 4 billion years old. So if we compare that to Earth, on Earth, Earth and Mars both formed about 4.5 billion years ago. On Earth, because of life and water and plate tectonics and the oceans and everything moving around all the time on Earth, most of the surface of Earth was formed in about the last billion years. We have some records on Earth because we can go dig wherever we want. we can go find all of the places where we have ancient rocks that are older than that, but we haven't found any rocks that are older than 4 billion years old. That's about our limit. And a lot of those rocks that are more than 2.5 billion years old have been really strongly affected by water going through them and life and metamorphism moving them and heating them up, and they're getting squished. And it's really hard to tell from those rocks exactly what environment they formed in. But we do know that we think life started on Earth sometime between 3 and 4 billion years ago. And so that's a time period we're actually very interested in on Earth for understanding what might have happened. Now, it turns out the entire Mars surface, basically, most of Mars surface formed during that same time. And the Mars surface tells us that we have records based on using different wavelengths of light to reflect off the rocks and tell us kind of what they're made out of. We can say that the earliest, the oldest rocks on Mars that are something like 4 billion years old, 4 to 3.5 billion years old, have a lot of clay like mud. And so they probably formed in a lot of standing water. Then rocks that are between 3 and 3.5 billion years old on Mars are really salty. We have really thick deposits of salt. And so it looks like Mars was drying up. And since about 3 billion years ago, it's been pretty dry. What that means is that, interestingly, unlike Earth, Earth has been changing so much. And so it's really hard to see this time when life started. But Mars actually might have a record of that time that's accessible on the surface, that can tell us about what our solar system was like during the time when life evolved. And so that's part of the extra excitement in going to Mars, is that, you know, Earth and Mars today are pretty different. But when we think back 3.5, 4 billion years ago, they actually could be quite similar. Earth was a different planet at that time. It didn't have oxygen in the atmosphere yet. And actually Earth and Mars may have been quite similar at the time when life started. And so all of these questions about the origin of life and what kind of chemical environment that might be in, we can actually start to understand what environments look like at that time by looking at the rock record of Mars a little bit better than we can sometimes on Earth. So when we send a rover to Mars, we have to pick one spot to go visit. That's actually a really big challenge, but I'll tell you about the spot we sent the Curiosity rover. The Curiosity rover, we decided to send to a place called Gale Crater. Gale Crater is about 110 miles across, the size of a good-sized city. And an interesting thing about this crater, you can see this is the diameter of the crater. And actually when the impactor hit Mars, and that was about 3.8 billion years ago, this meteorite came in, hit Mars. It actually hit the ground so hard that it caused part of the ground to rebound up and create a central peak in the crater. And we think that's what this pointy thing in the middle is. So the ground rebounded up, just like one of those slow motion movies of a water droplet or something. It rebounds up. And then a lot of this crater filled up with sediment. And we know that because of these flat layers that are exposed here, that probably most of this crater filled up, or at least half of this crater probably filled up with different sediment. And it was blown in by the wind, it was carried in by water. We see some evidence like over here for rivers that would have carried some in. But then later, the wind came back. And I've told you the wind had about 3.5 billion years to work, so it had a lot of time here. In this case, it had at least 3 billion years to work. And the wind has been blowing sand in from this direction, and it actually evacuated out part of the crater and actually exposed all these layers that record that early history of the crater. So these layers record when the crater first filled up, and then the wind has actually taken out a lot of material so that we can see those layers. So we have an exposure here that's just like the Grand Canyon or someplace on Earth where you actually get to see all of those layers. And so this is a great place to send a rover. You can see the wind is actually still working today. So the wind is blowing in from this side here, blowing this dark sand, which is actually kind of moving around that central area in the crater and actually right out the of the crater over here. So you can see the ground is a little darker over there because the sand is blowing across it, and the sand is a very dark color. This circle is where we plan to land with the rover. We landed pretty close to the X in the middle. And then we plan to drive up these layers. And we know from looking at these layers from orbit that those layers include ancient clays that tell us there was more water, and then layers of a lot of salt, in this case color-coded in yellow. And then above this line, a lot of the really dry, dusty material. And so these layers characterize some of the key units that we've seen on Mars and mapped out from orbit across the whole planet. So this was the place we wanted to investigate, and we got to send our trusty Curiosity rover. The Curiosity rover is the size of a small SUV. So this would take up a parking spot. It is not a small little thing. It's actually quite large. It's taller. It's about 2 meters tall. It's taller than I am. I realize you can't tell how tall I am in this video, but it's got 17 different instruments, or 17 cameras and 11 different instruments. And so it can take pictures and drive around and measure the composition, the chemistry, and the mineralogy of the surface. One of the cool instruments that stands out in this artist's rendition here is this laser. So it actually shoots this laser out of its mast, its kind of head here. It's got 2 cameras up here in this laser. The laser can shoot 7 feet away to about 20 feet away, and it'll zap a little spot on the rock into plasma, and then look at the plasma with different wavelengths of light and see what the rock is made of. So it's one of our reports of the chemistry of a rock. If we drive up to a rock, just like this rover has in this rendition, you can pull out this robotic arm. And on the end of the robotic arm is another high resolution camera, an instrument that can get the chemistry of a larger spot about the size of a penny. And what's extended right now is a drill. And that drill can actually drill about 5 centimeters into the rock and collect a sample. And then the rover has even more complex chemistry and mineralogy instruments on board. So it'll deliver that sample to different instruments on board. I'll note that this is not a solar panel powered rover. That's why it survived the dust storm last year on Mars. This is actually a thermonuclear, this is a nuclear power source, basically. So this is what's powering this rover and has been for the last 7.5 years on Mars. Now, we picked out the landing site. We've got our rover. The next step is actually getting to Mars. Getting to Mars takes about 8.5 or 9 months. And this is kind of a top-down view of the solar system. So how to think about how you actually would travel there. Well, Earth is moving around the sun in this direction, and Mars is moving around the sun 1 orbit further out. And so you actually have a chance only once every 2 years, where if you launch off of Earth, you don't go straight over to Mars because you've still got all that momentum. You're still going around the sun. The sun is pulling on everything in the solar system. So when it launches off of Earth, it actually takes this long trajectory over and intersects with Mars at a point about 8.5 months later. It has to travel quite a few million kilometers, millions of miles to get to Mars, even though in the end it might not be as far, as many miles from the Earth at that time. And so as we think about communicating with the rover and driving the rover, we have to keep in mind that it's orbiting the sun at a different rate than Earth. So sometimes Mars is behind the sun from Earth. Anyway, so this process takes about 9 months, and I'm gonna pause for a minute and show you a short little video clip of what it was like on the night that Curiosity landed. Now for me, I was hoping, I had just started my PhD and was really hoping to be able to do a project on this mission. For other people in the room, they had been working on this mission for 10 years. And you have to remember that we can't test the full landing sequence of how the rover will land on Mars on Earth at all, because we have different gravity and a different atmosphere. And so this was a very exciting night for us on August 5th, 2012.
Things are looking good. Coming up Planetary. Vehicle reports entry interface. At this time, it'll begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. We are standing by for guided start of guided entry. We are beginning to feel the atmosphere as we go in here. The vehicle has just reported via tones that it has started guided entry. At this time, the vehicle is beginning to steer its way to the target. We have seen peak deceleration. That is starting its first bank reversal. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Bank reversal 2 is starting. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Heat shield has separated. We've found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending. Standing by for backshell separation. We are in powered flight. We're at altitude of 1 kilometer and descending. Standing by for sky crane. Sky crane is started.
Signal to us, you remain strong.
Touchdown confirmed. We're safe on Mars. Time to see where our curiosity will take us.
Thumbnails.
That was a very exciting night for us. It actually landed perfectly. So despite not being able to test the landing system on Earth, it executed perfectly on Mars. And we were actually able to capture the landing. And so we at that time, NASA had 2 satellites that were orbiting around Mars. One of them was being used to immediately transfer the signal from the rover as it was landing back to Earth so that we would know what happened as fast as we could, which was, we were 15 light minutes away. So we were 15 minutes delayed on hearing about it, but that one was transferring the data back as fast as it could. And the other satellite that was orbiting Mars actually captured a picture. So it took 7 minutes from the top of the atmosphere to the ground. And this picture of Curiosity hanging from a parachute was captured by the Mars Reconnaissance Orbiter at exactly the time when Curiosity was dangling from a parachute at that exact location. So the engineering here is really incredible. We wouldn't be able to do any of this without the really amazing team of engineers. One other thing I wanted to point out, so this is a screenshot from the video, but you saw that Curiosity was lowered from this device, which we call the sky crane. And the sky crane actually carried the fuel that kind of shot out and slowed Curiosity down for just the last part of it reaching the surface. And in order to get Curiosity down on the surface totally evenly, it's shooting out jets, just like Iron Man or something, right? It's shooting out jets from these 4 sides. Curiosity actually had a camera right on the bottom of the rover. And so that camera took this picture while it was landing. And what you see is the dust being blasted off of the surface by these jets. And you see that there's one pile over here and one pile over here. And you'll notice that there's more dust being blasted off over here. Well, that's because the sky crane actually tilted to counter a little bit of horizontal velocity, which was partially because it was a little windy on Mars that day. So the engineers had really thought of everything and anticipated all of these potential issues and just executed the landing perfectly. And I included the link to the YouTube video down here, but you can search for landing on Mars, NASA JPL, if you want to see that again later. Okay, so once we landed, then the engineers who landed the rover, those guys in the blue shirts in the video, handed the keys over to the science team. The science team is about 400 scientists from around the world who work together to operate the rover on a daily basis, even today. So we're continuing to operate the rover. We meet about 3 times a week now and tell it what to do for about 2 to 3 days at a time on Mars. So one of the first things we asked the rover to do was take a full color image, a full color mosaic of that mountain in the middle of the crater. So we had been studying that crater for 10 years, 20 years even, some people, before landing this rover. And so when we got this picture, and it looks just like a place on Earth, right? We've corrected the coloring. The sky on Mars isn't blue, but we correct the coloring so that it looks the same as what it would look like if this location were on Earth, because that helps geologists figure out what they're looking at. So this is that mountain. And let me tell you, when this image came down, we had these TV screens at NASA, and we would all just stand next to the TV. I mean, there were just, scientists crowded in all around the TV screen, and we would just scroll back and forth and look at all the details, because it was so exciting to have these color images from the surface. And what we could see was that a lot of those layers we identified from orbit were visible here. These are the dark sand dunes that were gathering around the base of the mound that are actually blowing around the edge of Gale crater. This trough right in here contains the signal of clays from orbit that tells us that maybe water was pooling there, and maybe there was significant water at that time. Then we have a lot of these like very clearly defined layers. Those are the salt-rich layers. And then above this dotted line where the layers shift direction, those are mostly dry, rusty iron oxides, similar to what we see all over Mars today. So having landed, having taken this picture, we were so excited to see the layers. So here's where we landed. This is actually from the dust removal that I showed you. The dust was blasted out by the sky crane as it was landing. This is the direction that we wanted to go towards Mount Sharp from our landing site. And remember, we have 400 scientists, 1 robot, no roads. So if you've been on a road trip before with more than 1 human, you know that it is actually very hard to find the route that everyone will agree to take. And so interestingly, about the only time I think we've all agreed on which way we wanted to go was this first site, and we drove this way. So we drove kind of the opposite of the direction that we had planned. But what you'll notice is this is where the dust was removed. This is where we landed. This was the way we wanted to go. But only about 500 meters over here was this light toned patch of rock. And this whitish rock actually right here, so if you'll look, if you can see, these are the rover tracks. These arrows are pointing at the rover tracks driving across and over to this light tone layer. Now this light tone layer was the lowest topography in the crater. And so we said, well, if water flows downhill, water still flows downhill on Mars. So let's go to the lowest site and see if there's more evidence for water there. Plus, if you're looking at a history that's written in layered rocks, the ones on the bottom are the oldest. And so as you climb up the layers, you get to see younger and younger deposits. But it's really best to start at the beginning of the story. So we decided to drive over here first. That is an actual picture of the Curiosity rover when it's there. So keep in mind, it's basically the size of a car. It is a pretty big robot that we're driving around on the surface of Mars. And we actually do have high enough resolution cameras from orbit that we can actually see that car on the surface of Mars, which is pretty cool. Okay, so as we started driving over there, one of the first rocks we saw, this one was actually blasted clean by the sky crane. So this was affected by that dust blast removal. And what we see, it's called a conglomerate. What we see when we look and zoom in on this rock are a bunch of pebbles of different types. So there's a light tone one, there's a really dark tone one, there's a bunch of different pebbles, and they're all cemented together into a rock. Several of them are round. And so when we see rounded pebbles cemented together, we get pretty excited, right? It looks like a river. And so rounded pebbles are rounded by transport in a river. The wind won't round rocks that are quite this big. And then it must have been cemented by some kind of water passing through after that river to actually make it into a rock. And so we had never seen something like this on the surface of Mars, but this is clear evidence for water being transported across the surface. Now, the other cool thing is that based on the size of the pebbles, we can actually say how deep the water was. And this water was probably kind of knee to waist deep while it was flowing across this part of Mars, something like 3.5 billion years ago. So we were pretty psyched. We were like, okay, we're driving in the right direction. There was definitely water around here. As we drove along, we saw evidence for water in other forms. These are stratification, this layering indicates that this sand and these small pebbles were deposited by a river as well. And this came as we were approaching that light-toned area. Now, when we got to the light-toned area, we actually stepped down. I told you it's the lowest topography, it's the lowest area in that part of the crater. So we stepped down off this sandstone ledge where we were seeing all the river deposits. And I've kind of given it away here, but we got to a unit that looks like a mudstone. Now, you can guess what a mudstone might form in. But this was the point where we took out all the instruments of the rover. We said, all right, we're going to analyze this fully. And so just to give you a sense, we have a variety of instruments on the rover. We have that laser that I talked about. That laser can shoot little holes that are just about 300 to 500 microns across, very tiny little holes in the rock, and vaporize them and then tell us the chemistry of them. We have that other instrument on the end of the arm that will reach out and look at the rock up close. We have a camera, and then we have an instrument that'll get the chemistry. And that one gets the chemistry of the surface on a spot about the size of a penny. Then we can drill into the rock. And these are some pictures of our first drill holes on Mars. So this one was a little test drill hole, and then we actually drilled into the rock about 5 centimeters right here. When we drill into the rock, we collect the powder that comes out as we drill, and we can put that in instruments on the back of the rover. So we have 2 major instruments. One of them is called an X-ray diffractometer, but what it does is it shoots X-rays at that powder, and they get reflected off of the different minerals. So we have the chemistry, or the elements that are in the rock, and we have the minerals, or the way that the elements are bound together. So sodium and chloride and salt. We can also heat up the rock to about 1500 degrees Fahrenheit. And during that time, any water that got trapped in the minerals in the rock will come out. Any water or other kind of volatiles will come out of the rock. And so we'll look at that water, and we can actually learn about the water that was in the lake when this rock formed. And now I've given it away a little bit, but this rock formed in a lake. And one thing that was also really exciting, if you look at this, there were a lot of complicated instruments that we got to use on it, but also Mars has always been red. All of Mars' surface is covered in red dust. And so when we drilled into this rock and the powder that came out was gray, that was actually a really good sign just from the get-go, because red is oxidized iron and gray is reduced iron. And so this means that there are different forms of iron, and that's something that microbes on Earth use for energy. And so it's likely that this lake actually had energy for life. We looked at all the other data, and we determined that this lake would have been habitable for Earth-like life. The word habitable means a place where life could inhabit. And in this case, we define habitable as a place with all of the elements required for life, a place that had liquid water at the surface, a place that had a source of energy, and then a place that had conditions where the water was suitable for life. So not really, really salty water and not really, really acidic water, but instead water that was kind of like a freshwater lake on Earth. So this was a freshwater lake on Earth, and the final requirement is that you have to have all of those conditions for an extended period of time. And so we think this was basically a freshwater lake that sat on the Martian surface about 3.5 billion years ago for something like 10,000 years. So this discovery kind of revolutionized our thinking about Mars, right? We had seen that water had crossed the surface. We had looked at a couple of places where water had interacted with the rocks, but to see from the ground a site where we can say there was a lake 3.5 billion years ago, where if Earth-like life or fishes or microbes had been on Mars at that time in that place, they could have survived. They could have lived there and thrived. Now, we haven't found life on Mars yet, but the first step is saying that there were environments where life could have lived and survived. And we can send different kinds of instruments, or we can bring Mars rocks back to Earth to analyze whether there could have been life. Here we do have all of the elements required for life, and we have found small carbon-based kind of molecules, probably molecules from space. They're very small. They're not kind of Earth-like. They're not living organic molecules, but they're carbon and hydrogen bound together. Okay. So now that we have the start of the story, we were so excited to see, what else was there. So remember, this is the lowest layer, and now we're going to climb up back through those river sediments and see what comes next as we climb up the mountain. So we turned around, we looked over at the mountain. It's so appealing. It's beautiful. I love these images. I put them on the back of my computer. I stare at them all the time, but these beautiful layers of rock that are going to tell us the story of Mars history. And so we saw those layers, we just started booking it. We were like, well, this ground is pretty flat. Let's just book it over there, drive as fast as we can. A month or so in, we happened to take a picture of ourselves, and we saw that the wheels had some holes in them. So this was a rough moment. We paused, we stopped the rover. We said, how did the wheels get so beat up? They haven't been driving that far on Mars. And it turns out that after 3 billion years of the wind blowing sand across the surface, a bunch of the rocks at the surface of Mars were quite sharp and pointy. And we had developed the wheels so that they would be low mass, so they wouldn't weigh too much, and they would have a large surface area. So we were trying to make sure that if we got stuck in some sand, which we knew was a possibility, that we'd be able to get out. We didn't think that the rocks on Mars would be quite that sharp. And so this required a lot of studying. We went to JPL, we had a bunch of copies of these wheels made, and we started driving them on all different terrains so that we would understand exactly how is this wheel going to fall apart if it keeps driving like this. And we kind of figured out which kinds of rocks to drive over to make sure that we wouldn't continue to damage the wheel too much. And once we got to the point where we said, okay, I don't think the wheels are going to be the first thing to break, then we decided we'll keep going. I mean, there's nothing you can do to fix this rover, right? It's on Mars. There's no mechanic you can visit. So the fact that it's been up there for 7.5 years and still going is awesome. And the fact that we can figure out ways to minimize ongoing damage, well, that's the best we can do. I did want to point out one more thing in this image. You'll notice these holes in the back of the wheel right now, and there's some of them in this other wheel as well. Those holes are just meant to be different from the rest of the tread, so that as the wheel goes a full circumference as it drives across Mars, if you look back at the rover tracks, you can see one thing that's different. And every time you see that record, you know that the wheel rotated once, and you can see the distance that the rover has driven. So we wanted one part of the wheel to be different. Now, the Jet Propulsion Laboratory at Pasadena, California was designing the wheels, and they wanted it to say JPL. So that as the wheel drove across the surface, it would say JPL, 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 right? And NASA said, you can't brand Mars. You can't just put your name all over it. So they said, okay, we'll just put in these different holes, and that's when they put in these holes over here. Now, as soon as the rover launched and was on its way to Mars, JPL did a little press release and said, by the way, that says JPL in Morse code. So that's what those holes are, is that they actually are just JPL, JPL, JPL across Mars. So you know how many times the wheel has rotated. Those ones were intentional. These ones were not, but we've been working around it. Now, one of the ways we work around it is we ask a bunch of experts, scientists, you know, which path should we take? We're working on a team, like I said, 400 scientists, one card. I'm just going to give you an example of a slide that has come up in a meeting. So we were trying to get from point A to point B, and we asked 5 experts, what is the best path where we will see interesting science and we will keep the wheels as safe as possible? I don't know if you can see, but there are 8 paths, and one of them does not go to B, right? And that's kind of what collaboration is like. But I just kind of wanted to point that out. This is always a challenge, and we are literally meeting, you know, we're still meeting 3 times a week, deciding every day everything about what this robot is doing. So we have to decide exactly which rock we will shoot with the laser and which rock we will drive up to. So there's a lot of decisions and a lot of international teamwork that goes into this, and it's really a privilege to get to work with so many different people who are so excited about their jobs and who work together to keep this rover safe and help us learn as much about Mars as we can, even if some days look like this. Okay, so as we're driving, we took the pink path, by the way, if you looked. As we're driving, we get to see these beautiful rocks, and I'm going to tell you about one of them. This is a set of rocks, and we're looking at the same set of rocks from 2 angles. So this is kind of a side view of these rocks going away from the crater rim and towards the middle of the crater. From here, we're looking head on. So the rover is sitting over here and looking towards the middle of the crater. And you see all these rocks kind of lined up in front of you, and they're all kind of dipping down towards the middle of the crater. This unit was kind of one of our key units for figuring out that this was also, even though it doesn't look the same as that other site, I showed you Eberswalde crater, where the river comes into the lake and deposits all its sediment because it's coming into a lake. This is the same thing. We don't see it the same way, but if you look at this top picture, and I have a model here, the rivers are coming in this way, and as the river enters the lake, we call that area where it drops all its sediment the delta. And as the river enters the lake and deposits all its sediment in a delta, it tends to leave this kind of swoosh shape. And what you're looking at in these rocks is just that shape. So these rocks are part of a delta when a river was entering a lake. And we were excited about this because we did actually drive across quite a few river sediments, and we were hoping to find another lake. So after we saw this, we knew we were heading in the right direction, going towards the middle of the crater. And sure enough, once we reached kind of the base of that mountain, we saw lake sediments. And so these are the kind of rocks that were deposited in a lake. They have laminations, and so they're these very flat layers that extend, oh, whoops, my hand disappeared, that extend for a long distance across the surface. So the lake was very flat, very calm, and probably a decent size. And as sediment kind of comes in, whether it's coming from the wind or coming from a bunch of rivers, it deposits a layer of sediment, and then maybe in the next storm or in the next season or maybe each year, there's a new layer of sediment deposited. And because there are different seasons, sometimes those layers look different, and we actually get this record of layers of mudstone deposited through time. Now you can see over in the right picture, those are just millimeters thick, and over in the left picture, they're centimeters thick. So this lake lasted a while and had kind of different events happening where some years had more sediment and some years had less sediment maybe, or some storms, or maybe this was closer to the edge of the lake and this was closer to the middle of the lake. We've got a few things still to figure out. Okay, so we found this lake, and we've been looking for it for a long time. So we started driving up the lake and trying to tell the story of each layer in the lake. I'm going to show you some overhead pictures and then a side view of what we've been driving through. Okay, here's an overhead picture. These are those sand dunes that are tracing around the mountain. This is our path. So we landed right off the top of the screen here. And then we've been driving and coming up through here. So So this is our path up the mountain. This is a layer that I'll talk about a little more. This is a ridge, and then this little trough, and we're right over on the other side of the trough right now at that yellow star. Let me just color code this. Okay, all of this light blue area was mudstone. All of it was deposited in a lake. All of this layer was also mudstone, also deposited in a lake. And the purple turns out to also be mudstone, also deposited in a lake. And so if I give you a side view of what that looks like, we were climbing, here's where we landed. We went over to that little lake that we saw at the very beginning, and we said, oh, we're in a habitable area. Oh wait, I should note, this is the distance traversed by the rover, and this is the elevation it's climbed. These are not to scale. There's a vertical exaggeration of 14. So we've stretched it so that you can see what we're talking about. But so the rover doesn't climb up slopes quite this steep. But we saw those river sediments for a long time. And then we reached the mudstone right here. We reached the lake, and we've been climbing and climbing and climbing through lake sediments all the way up to here. That means that there was a lake on Mars, not just for 10,000 years, like we thought before, but instead this lake could have lasted for millions of years. And so we are still trying to kind of figure out all the different parts, but it's really been really exciting. I mean, this is transforming our view of Mars. We thought that maybe there was liquid water for short periods of time, or it burst up to the surface. But to say instead that there was a lake for maybe millions of years, we're really trying to reevaluate all of our climate models and how was Mars that warm, even though it's farther away from the sun, and the sun was actually less bright 4 billion years ago. Okay, since we've reached all the way up here, we're pretty proud of ourselves. And I don't know about you guys, but when you're proud of an accomplishment that you've done, you might take a selfie. So this is our recent selfie from one of our climbs. So here's Curiosity. At this point, it's been on Mars for 7.5 years, and it's accumulated a little bit of the red Mars look. So it's gotten quite a bit of dust on it, but it's still going strong. You can see a couple holes in the wheels if you look right over here, but it's still doing great. One of the things that's showing off in this selfie is that it's just drilled a hole to see what this rock is made of. And you can see even from here that that hole is still showing that the sediment is gray, the rock is gray. And so we still have that energy we needed for life. Okay, one other thing about this picture is that the arm is missing. I told you there's a little camera on the end of the arm that's just supposed to be for when we look up close at rocks and we want to get a high resolution picture of the surface. What we do instead in this case is take that arm, put it as far away from the rover as we can, turn that camera back to the rover, and then start taking these pictures. But it's a very small area camera, so we have to actually take about 60 or 80 pictures and move the arm in all sorts of configurations to try to get the whole rover in the selfie. And that's why in the end, you actually don't see the arm at all, because we've taken the pictures from so many different angles and then had to stitch them together really carefully. So now, even though the rover's in isolation, it manages to take selfies of itself and send them back as postcards to us on Earth. Okay, now I'm going to show a quick video again, and I'll talk over this one. But this is to tell you how we've pieced together the story of what's happened in this crater through time. And so I'm just going to pull together the whole story I've been telling you. 4 billion years ago, there's the ground. And about 3.8 billion years ago, there's a major impactor. I told you there's this big rebound peak in the middle of the crater. And after the crater formed, water started coming in. Water may have come in from groundwater, but it also came in over the edge in rivers. And that water was carrying sediment. So we deposit conglomerates or pebbles, sandstone, and a lot of mudstone as that water kind of keeps coming in from the edge. Now the upper part of the crater looks pretty dry, so we don't think that water necessarily filled the entire crater. Maybe that water dried up, and later the wind blew in extra material. So the wind might have blown in a lot more material, could have buried all of these sediments, definitely covered this part of the crater. And then eventually the wind changed direction. That could just relate to something with Mars orbit, but it started evacuating the crater. And the wind actually evacuated deep into those different layers that we saw. So that's how we get this beautiful record. We know that there was also water at different times during this story. So we've shown water kind of reaching up through different cracks in the ground. And then in 2012, a rover appeared on the surface. And that's the rover we're following. And as you can see, it actually gets to explore all of these layers that were deposited 3.5 billion years ago because of that wind event kind of evacuating out the crater. And so as we're driving through, we're looking at those layers from that lake and realizing that there was a lake in the crater for a long time. Okay, so just one more visual of that, but something like 3.5 billion years ago on Mars, there's a significant lake in this crater. I actually have one point I want to make with this picture, and that's that the central peak is missing. So this is an artist's rendition, but there should be an island in the middle where that central rebound peak came up out of the ground. Okay, so just a couple more things. As we've been exploring, we've been continuously taking those drill holes and analyzing the sediment. And so we're piecing together the story of what happened in the lake in a mineralogical way, as well as in this physical way. And these are some of the drill holes we've drilled. You can see that it changes color. Sometimes it is reddish, sometimes it's lighter. And we're still working, this is what scientists are working on today, is trying to figure out what was the record of that lake. But for the most part, so far, we think that that lake was habitable for just about all of its existence. And I'll tell you a couple other things. My group at Rice University is working on, we're interested in understanding that mudstone and understanding the river rocks and thinking about them from the perspective of, there used to be volcanoes on Mars that deposited a bunch of rocks. Those rocks were broken up and then carried in water, ice, or wind down into the crater. During that process, the different rocks might have been sorted, and then they were deposited, and then they were cemented, and they became the rock that we see today. And so we just try to figure out, can we tell the story of the volcano? Can we tell the story of the transport? And can we tell the story of the lake water chemistry from what we see in the rocks? And so one rock that we've studied is this rock. On the Mars team, because we look at rocks on Mars all the time, we give them names. So this rock is named Harrison. Harrison is about the size of your fist. It's 6 centimeters across, and it is a volcanic rock. So this one came from a volcano. And what you see when we zoom in on the middle of this rock is that there's these light-toned, long crystals, feldspar crystals, that formed deep underground and had a long time to cool. And then all the other crystals in this volcanic rock are very small. And because of the grain size difference here, when we look at rocks deposited by rivers on Mars, they have very different chemistry because these long grains get trapped in higher energy areas, and then the small grains come out in the lower energy areas. Another thing that we've been working on, David mentioned that sometimes we go to different places on Earth that are kind of like Mars. And so one of the places we've investigated, this is one of my postdocs, Michael Thorpe, and he got some samples from Iceland and from Idaho. And so when we're looking at the river rocks on Mars and the mudstones on Mars, when rock interacts with water, then some components of it dissolve away. And so we look at how much has been dissolved away to try to figure out how warm the water was and how long it interacted with water. And so we have this kind of index for comparing that. But the idea of this is that anything below here is you're looking colder, and then you go up, and these are warmer climates. And so when we look at Idaho, it's quite warm on this scale. When we look at Iceland, it's quite a bit colder than Idaho. And Mars is kind of even colder than Iceland. It overlaps with Iceland. So we're pretty excited because we see areas where life could have lived for long periods of time on Mars. But we should also keep in mind that it was probably very cold. And there was probably a lot of ice involved, except we don't see too much of it inside the crater. But it was probably very cold and icy. And so anything like the start of life or life moving on, it would have been very cold, a little colder than Iceland is today. Now there are a few parts of it that are warmer and are closer to Icelandic climates, but hopefully that gives you kind of a sense for what we're thinking of for this lake on Mars. Okay, and I just want to tell you a couple things about where we are right now. We've climbed up the hill. We're in this little trough where from orbit we could see a lot of clay. So we're in an area we could tell water interacted here. Now it turns out almost the whole side of the mountain that we've climbed up has been mudstone. So water was definitely involved. But you can see it's got some beautiful sediments. And we actually have a picture. This is from a satellite again, showing Curiosity investigating those sediments. This was that ridge with a slightly different chemistry, and then we're in the clay unit, which is this trough. And there's the little rover. You can actually see its head and its 6 wheels. So these are pretty impressive images. And we recently snapped this beautiful panorama, which I would recommend investigating further. But here you can see the tracks of the rover driving up to this site. And you can see this is actually the wall of the crater. So this is actually this is about 30 miles away, but Mars doesn't have very much air, and so it doesn't have too much air pollution. And so you can actually see about 30 miles away where the wall of the crater is. And then you can see some of the tracks and some of the areas that Curiosity has looked at while climbing up this wall. One more beautiful picture from 2 weeks ago. Just investigating we're getting closer to these cliffs. Some of this was deposited when there was either a landslide or a river that kind of slid stuff down from the crater center, from the central peak of the crater. And then finally, I wanted to show you one more image. This was taken 1 week ago. So this is one of the most recent pictures that we've gotten back from Mars. And one of the coolest things is that NASA says that everything that they do should be available to the public, that it's publicly funded, it's a government organization, and they want everyone to be able to share in exploration. And so every image we take on Mars is immediately available to the public. And so like this picture, it's only been on Earth for 1 week. You guys are some of the first people to look at this picture. You can explore a new part of Mars every day by seeing what pictures have come down from the rover. And if you click on what pictures have come down that day, you can be in the first few hundreds of people that actually see something on Mars that we've never seen before. And so that's one of the most exciting parts of this job. And you can just go to, I put the website link here. Oh, my PowerPoint just crashed, so I'm not sure what you guys are seeing, but I will open up PowerPoint again.
Kirsten, we're seeing your computer screen, which has got the rover panorama, the selfie
oh,
in the
good.
background.
So we've still got Mars.
Right.
Here's a different drill hole we were quite proud of. And let me get this back just to wrap up. Nope, other side. There we go, we good? All right, so this is one of those most recent pictures, and I just think they're beautiful. Okay, and last thing, I want to tell you about what's coming next. So in July of this year, July of 2020, we are sending the Perseverance rover to Mars. It just got a new name. There was a naming contest for schools, for students. And so we just got the name Perseverance, and it will launch in July. They've just put the wheels on, and they're packing it up to go over to Cape Canaveral. Now the Perseverance rover is the same size as Curiosity. It's also nuclear powered. It has better wheels, and it has a different purpose. So this rover has a different set of instruments. Instead of having all of those laboratory instruments on the arm, it has this larger device, and it is a drill, but it can drill into the soil and collect a core of rock. So it's going to kind of drill out the center of the rock and collect a piece of rock the size of your pinky. It'll take that little pinky-sized rock and put it into a special sample container, and then it'll go around and collect several of these. It'll collect about 3 dozen pinky-sized rocks that we're excited about from Mars. After it's collected those 3 dozen pinky-sized rocks, it will put them in a pile on Mars and drive away. Then another mission will come from Earth. It'll come over, it'll land near the pile. It'll send a little rover to go grab the pile of sample tubes, bring them back, and launch them from that base pad into orbit around Mars. A third mission will come from Earth, grab that special payload in Mars orbit without ever landing on Mars, and bring those samples back to Earth. And so Perseverance is the first mission where we will get to sample rocks from Mars and actually bring those rocks back home to Earth. And so we are really excited. If any of you are students, we're talking about samples that will come back in something like 2030. And so we're really looking for, you know, the next generation of researchers that will actually be able to touch rocks from Mars. And so you guys could do your PhDs with rocks from Mars. You guys can develop the instruments that will be able to analyze those rocks. We're going to have a whole new set of samples. And so we're just really excited about this mission and what it means for future generations of scientists. It's going to go to this area. This is called Jezero Crater. And you can see this is in line with that story I've been telling. There's a river that entered the wall of the crater right here. And it turns out there was a lake in the crater because as soon as that river entered, it dropped all its sediment into another delta. So this is another delta. The color code here is just because we've discovered a lot of minerals that we could see from orbit that tell us that this is the distinctive place on Mars that has a lot of the rocks that do a good job on Earth of preserving fossils. And so our goal is to be able to sample some of those rocks, sample some of the volcanic rocks, sample some of the different rocks around this area, and start to tell more of the story of Mars. Capture if there could be life, capture what the volcanoes were like on Mars, capture, you know, more of that story in a way that we can't possibly do with just rovers on Mars. If we bring those samples back, when we bring those samples back, fingers crossed, we'll be able to analyze those rocks with every instrument ever developed on Earth and the instruments that get developed in the next several decades. And so this is our really exciting next step for learning about Mars. And so I want to just thank you guys for your time. It's really a privilege to get to talk to so many of you from across the country or around the world. So thanks for logging in. I want to give you one slide next, and I'll just kind of pause on this slide. I'll wrap up my talk, but pause on this slide, and I've tried to put a whole bunch of links for different online resources. I don't know exactly how this will show up on your screen, so I can maybe copy this into chat as well. But there's a lot of online resources to learn more about Mars. I pointed at a couple of YouTube videos from NASA JPL, but there's a lot of educational resources available. There's virtual reality tours of Mars. All of the images we take are available. There's a whole lot of education activities. Google Earth can switch to Google Mars. So if you want to keep learning about this or you want to follow along with the mission, you know, take a screenshot, get these links because it's really fun. It's really exciting to get to participate in space exploration, and that opportunity is available to all of you. So thanks for tuning in, and I'll be happy to take some questions through the Q&A.
So thanks, Kirsten. I know you can't hear people clapping, so I'm going to clap for them. I think that was fantastic. So, and my daughter's here clapping as well, so that was great. So here's the deal. We have over 50 questions, which is great. And because of we weren't able to sort of interrupt during it, obviously the earlier ones are from way back in your talk, and then there's later ones coming in. So with the risk of offending some people, what I would like to do is go through them and maybe do every third one, and then if you're up for it, go back and recycle through. Okay. And if it's possible, if you can give a short answer, that will allow us to get through more of them, but you're in charge of that. So if we go way back to the beginning, and because people can't shout at me, I'm free to do all of this, so I'll just ignore the chats. So one of the very first question came in before you even got started, was from somebody called Owner, so I don't know who that is, but has what we recently learned about Mars rock changed how we identify possible Martian meteorites on the Earth?
Okay, yes. So I talked about Perseverance, which will bring the first samples that we've selected on Mars back to Earth. But it is also true that every now and then a meteorite hits Mars, or something hits Mars so hard that it knocks Mars rocks off of the surface, and some of them actually come over and end up landing on Earth. And so we have several meteorites that came from Mars. And actually, most of them have been identified based on some of the data we acquired with Viking in the 1977 and after. And so what we do is we just look at when it gets knocked out of the Mars atmosphere, some of the atmosphere actually kind of freezes in a glass onto the rock itself. And when we get meteorites from Mars on Earth, we can look at that glass, and it has the same elements and isotopic composition as the Mars atmosphere. Now, because it's actually just what the Mars atmosphere is today that matters, those first measurements that we took in the 1970s from Viking have pretty much identified what, at least gave us a first order check on what all the elements and what the composition of the atmosphere was. And so most of the meteorites that we've seen have been identified that way, comparing them to those measurements.
So Kirsten, we're now up to almost 80 questions. So I'm not quite sure how, so I'm going to apologize right now for the questions we do not get to. I apologize for that.
Yeah, sorry guys.
You know, I think this is, giving a talk for an hour as we're getting used to Zoom is actually quite tiring, as we've been giving classes all day and stuff. So, so let me work through. Robert Cunningham says, is Everswald crater what made the what made the deposits less resistant to erosion?
So I'll pull up that slide. So what made the other areas less resistant to erosion is probably that they were very fine grained. So it was probably mudstone that was depositing in the bottom of the lake in general, but right where the river came in, it deposited sand and pebbles. And so those are a little bit harder to erode usually. And so that's probably what, so what's left here standing tall are the sand and pebbles.
Thank you. And then from Kirk Carver, can you reiterate how we know the older soil is clay? What technology was used?
Yes.
And for those of you, I'm putting a dot in the answer because then it removes it from the list of questions. So I'm not typing an answer, I'm just getting rid of your question from the queue.
So when we have satellites that are orbiting around Mars, and what those satellites do is they use different wavelengths of light, and they reflect, actually the one that can see clay is using sunlight reflected off the surface of Mars and taken in, and it's called a spectrometer. And in this case, it's looking at wavelengths of light between about 400 nanometers and 2,500 nanometers. And in between, in those wavelengths, there's some bonds in clay minerals. So it's actually, there's clay minerals and there's clay grain size. There's certain bonds in the clay minerals like hydrogen to oxygen, or silicon to aluminum. There's different bonds in those minerals that will actually absorb certain wavelengths of light. And so when those wavelengths of light bounce off the surface, they get absorbed by the clays. And then when you look at what wavelengths actually reach the instrument from that part of the surface, those wavelengths are low. And so we use kind of signatures of different minerals in that set of wavelengths to detect where they might be on the surface. And we have several instruments with different wavelength sets that help cover different types of minerals. But clays in particular, we use, it's called the CRISM instrument, and it's that set of wavelengths.
And this is from an English professor in Colorado. Where did all the water go? All this water that you were talking about earlier on, where did it go?
Yes.
So that was Richard Johnson. It's not just an unnamed English professor. It's Richard Johnson is his name.
Okay, great. So it's a great question. I'm actually teaching an entire class this semester where we are trying to figure out at least what we know about the answer to that question. One part of it is that there is actually enough water at the two poles of Mars that if you were to completely melt the polar caps, you could have enough water to cover all of Mars in 22 meters thick of ocean. If Mars were a sphere, we actually have that much water in the poles today. So some of it is just frozen, and the atmosphere is so thin that today you can't actually go from, you can't have liquid water. The air pressure is too low. It only goes from solid to gas. A lot of the water also was lost to space. So Mars does not have a magnetic field like Earth. On Earth, we get to see the magnetic field interacting with the solar wind when you get to see the northern lights. So there's solar wind blasting in from the sun, and that's all just being ejected from all of the different reactions that are happening at the sun's surface. And that solar wind will blast into Earth, but because of our magnetic field, Earth is mostly protected. Earth's atmosphere is protected because those ions get deflected. On Mars, there is no magnetic field. And so instead of being deflected around and protecting Mars, they're only deflected because they bounce off of parts of the Mars atmosphere. And when the solar wind is blasting over and bouncing off of parts of the Mars atmosphere, it takes a lot of hydrogen with it. It sometimes takes oxygen or water with it. And so a lot of Mars atmosphere was lost that way. And maybe a lot of it was lost pretty early on. So around between 4 and 3 billion years ago.
So this comes from Timothy Baba, University of Nevada, Las Vegas. For the dark sand dunes, could you explain the dark color?
Yes, so a lot of Mars is this kind of palish red because we have this dust that's just settled all over the surface. And every 10 years or so, we have a global dust storm where a bunch of that dust gets kicked into the atmosphere and lands on the surface again. And so because that dust is just always being deposited everywhere, most of the surface of Mars, you're just seeing that dust. And so that's why it's all so reddish. The sand is from basaltic igneous rocks. So it's the kind of volcanic rocks that you have in Hawaii or Iceland. They're very dark volcanic rocks. And that's what most of Mars was made of originally. But as those break up and they turn into sand-sized particles and get blown by the wind, those are some of the only parts of Mars that don't have dust on them. And so you can actually see the dark color because the sand grains are moving around enough that they're not as dusty as the rest of Mars.
This is from Forrest Anthony, I think. It's when you were talking about, I'm paraphrasing it a little bit, when you were talking about the kind of elements that you were looking for with respect to potential habitability, those conditions. He's asking if the mudstone has enough signs of nitrogen and phosphorus. Was there any signs of nitrogen and phosphorus? Of course, is what we need for life here on Earth.
Yes, yes, absolutely. So those elements are SNOPs, right? They're carbon, hydrogen, oxygen, phosphorus, sulfur, nitrogen. And there actually is more phosphorus on a lot of parts of Mars than there is on Earth. So phosphorus would definitely be available. And with the mass spectrometer, where we actually heat up the samples, we look at the different states of nitrogen, and it looks like some of it, we've seen some that's oxidized in different states, so it might also be bioavailable nitrogen. So interestingly, we actually do have those elements and in the forms that organisms take in or create on Earth, which is actually, it's kind of surprising, but cool.
Here's an interesting one. Kirk Carver is saying, how long will it take for the gray drill dust to oxidize back to reddish?
So that reaction typically requires at least a little bit of water. So I think it would take a while for the gray dust to oxidize. There's a tiny, tiny bit of water in the atmosphere, and sometimes Mars orbit, like Mars, the planet, kind of tilts at different angles relative to the sun. That's on the hundreds of thousands of years timetable. And those different tilts might cause the polar caps to move to different parts of the planet. And that, we think, has had some effect on helping oxidize a lot of the surface, or having water to react with a lot of the surface. But I suspect it will take quite a while until there's a little bit of water to help that reaction.
So there's a few questions that I've kind of passed over, but I think it's about plate tectonics. So if there isn't any plate tectonics on Mars, how was there volcanoes? Were they just hotspots? But other people have asked whether there was plate tectonics ever on Mars, and if not, why not? So just a generic plate tectonics question.
Yeah, so Earth has plate tectonics. We actually don't know exactly when Earth's plate tectonics started. So we don't know for sure if that was 3.5 billion years ago or 2 billion years ago. There's just different ideas for that. so actually, the funny thing is that the question ends up being, after we look at the whole solar system, it turns out Earth is the only planet with plate tectonics. And so Earth is the only planet where there are plates gliding around on the surface and sometimes getting pushed and subducted under each other. Whereas on Mars, we don't see any plate tectonics. There are volcanoes, and they are essentially hotspots. And because, because there aren't tectonics, the hotspot will kind of stay in one spot, which is why Mars actually has the largest volcano in the solar system. It's part of why Mars has the largest volcano in the solar system, right? Olympus Mons is 3 times the height of Mount Everest and essentially goes out of the atmosphere of Mars because you had a hotspot that just kept being in the same spot. One thing that I'll note, and it shows up in this picture, which is why I pulled it up, is that there are this long straight line. This canyon is called Valles Marineris. It would go all the way across the United States. It's huge, and it's 3 times or 4 times as deep as the Grand Canyon. And that is probably tectonic action in that there was either a major impactor and or a bunch of volcanoes in one spot that made one part of the crust so heavy that the crust actually kind of split in this other area. So there can be Mars quakes, but there aren't plates the same way we define them on Earth, and there's no subduction where one plate goes under another plate. But there have been parts of the crust that have been split by the weight of the volcanoes, which are huge.
And then Phoebe Tang asks, can you explain again how the gray iron powder indicates that there's energy for life?
Yes, so life on Earth can be powered in different ways. So since we have photosynthesis, we have a lot of our organisms get energy from the sun, and the sun actually like powers a reaction that creates that then allows the molecules to store energy. But before that, and in deep environments on Earth, energy or life gets energy from reactions. And those reactions go from oxidized and reduced states. And so the thing with the gray rock versus the red rock is just that we thought that all of Mars was oxidized, and we thought that it was possible that oxidation had gotten quite deep on Mars, or at least several centimeters deep, and that it would be hard to ever see if anything was still reduced. And so as soon as we drilled it and we saw that it was gray, the main thing that colors the rocks is iron, and iron in particular, just because of its character, it's red when it's oxidized and gray or kind of greenish color when it's reduced. And so as soon as we saw that rock was gray, we realized that it didn't contain as much oxidized iron. It doesn't take very much oxidized iron to color a rock red, but if you've seen red rocks out in like the Western United States, those are all colored with iron. And then you can easily see bleached zones or areas that are grayer, and those are all reduced iron. So iron just happens to dominate the color of a lot of rocks. And so when we saw the gray, we knew that there were multiple states. And as soon as you have those multiple states on Earth, there are some microbes that could live off of the energy difference between the oxidized and reduced iron, or exploit that for energy to survive.
So we still have 80 questions left, Kirsten, so I think we're not going to get through them all. But I want to combine a couple from Bhavan Rajan and someone with the username Danro. And it's basically about what are the current explanations of how liquid water could have existed and how the planet was once warm. And then the other part of that question is there an estimate for how much water may still reside inside the planet, not just at the poles?
Yes. Okay. So the water would have gotten to Mars early in planetary history. So planets accrete. So the sun forms first, and there's just orbiting dust clouds all around the sun. And those dust particles start to collide with each other and grow bigger and bigger, and you end up accreting these pebbles, and the pebbles are orbiting the sun, and you get asteroids, and you get bigger and bigger things until you build entire planets. And during that phase, these planets, both Earth and Mars, were probably too close to the sun to catch very much water, because water that close to the sun would be a gas. And so they could only hold on to a little tiny bit of water because it would have just been a gas and gone out further, which is why if you go out to Pluto, you've got tons of ice, because all the water suddenly became a solid when it was out there, and it accreted and created icy bodies. But these planets were probably mostly dry at that point. But then because of asteroids and comets that would have come in from further out in the solar system, they actually collected chunks that would have been icy. And so they collected chunks that would have been out further, maybe by Pluto, maybe by Jupiter, that would have been icy, and those added water to the surface. Whether Earth and Mars accreted the same amount of water or different amounts of water isn't really known. Well, Earth would have gotten more because Earth is bigger. But they probably both had a lot of water at the start. And probably Mars just lost it because of that lack of a magnetic field and because it had less gravity because it's quite small. And we think that there still is some amount of water in the middle of Mars, and that would come out whenever volcanoes erupt. But it's really hard to figure out exactly how much. So a lot of the meteorites we have on Earth indicate that, well, they have just totally different answers. So some of the meteorites say that there's almost no water inside in the lava that's actually coming out of Mars. And some of the rocks say that there's more. And so what we think is that there's some parts of Mars that had more water and some parts of Mars that have less water, even on the inside. And then the other question that came with that was that there is some ice under the surface of Mars, anywhere near the two poles, and that could add up to another 5 meters or so, at least, of water if you were to melt it all and put it all on the surface and Mars were a perfect sphere. I told you the two poles would be 22 meters. With that additional water that we can see, you'd have more like 30 to 50 maximum, but there could also be water that we can't see that's deeper than our instruments penetrate.
This is a paraphrased version from Stokes Macmillan. Is there any evidence of liquid water on the surface of Mars today?
There's a few things that look intriguing. We don't really think that there shouldn't. I'll show you a couple things that look intriguing. You hit some of my extra slides. In the summer on Mars, in some craters where the walls get relatively warm, we see these dark streaks that form on some slopes and then slowly over the course of several months slide down into the crater. And it looks dark and it looks like maybe it could be water. And the only way to have water is to have it be really salty. If you have really salty water, then at this pressure, you might have a little bit of liquid water. But the current thinking is that these are still probably dry. There's a lot of debate among scientists. So this is one of the things that we talk about is this evidence that there's enough salt in some areas to create a little tiny bit of liquid, to create some instability so that these dark streaks slide down. Now, I answered a question earlier about how dark the sand was in the crater, and this could also be a similar effect. So anything that's not as dusty looks really dark. And so if sand just slides down for some other reason, it will also leave a dark streak. But it's one of the intriguing things. And there definitely is ice at the poles, and some folks think there could be water at the base of the ice. Other folks have pointed out that that only really makes sense if there's also a volcano right under the ice, because it shouldn't be warm enough even at the bottom of the ice. So there's still a question there.
So I'm not sure if I can read out all of these names. There was a bunch of questions I just passed over about perseverance. Mm-hmm. A couple of people, including Pat Rife at Rice and Michael Zumalin and Sam Knappen wants to know if the wheels are different and will they be more robust. And then there's what will the bootleg stamp be? I'm hoping it says Rice, but I'm sure it won't. But you know, the JPL Morse code equivalent, is there going to be a sneaky hack for that?
Yes, some of that we will find out, I'm sure, after launch and or once it's on the surface. I know there are a couple. I'll say that. I won't give them away. That's for the engineers who built it to tell you about once it's landed. But I will tell you that you can look forward to finding a couple of little surprises on the rover. The wheels though are they are different. They are thicker and they have a different tread pattern. And I don't think they have any I think we don't have a distinctive side, so you won't get that JPL imprint across the surface, but hopefully you also won't get holes in them. So
I'm trying to look for. I'm having to select questions now. There's just too many. Oh, all right. I have. Okay, I'm going to ask another wheel question just because it's my daughter and she just punched me in the arm. What did you guys change on the wheels to make sure that they stay intact? What was the change that you made?
they're thicker and the grousers are designed differently. So you can see in this picture that there are straight lines across them, straight lines across the wheels. And so those are the thick parts are called grousers. And that on this case, there are more grousers. So there's less thin sections in between the grousers. And the way they've got a little bit of a wave, actually, they're not perfectly straight. So they'll still provide kind of a different level of traction, but all of that is very carefully engineered by the folks at JPL who first practiced driving wheels over all different terrains, and they say these will be more robust, and they are thicker. So the previous ones were actually quite thin. It's kind of embarrassing when we just say it, but they're about the thickness of about 3 aluminum cans. So they are quite thin and made of aluminum, the ones on Curiosity. Now, like I say, that made sense for our original goal, which was that it would be able to get out of sand piles and that it would land safely. We just didn't know quite how hard and sharp these rocks would be.
So this question comes from Nancy Glass. How do you get to be one of the 400 scientists who work on the rover? I think maybe this is partially how did you get to be one of those, but then also how do you get to be one of those coming forward?
Yeah, so there's a few ways you can get onto that people get onto the rover missions. One of them is that they design an instrument, and NASA has a selection competition. So some people propose a mission, some people design instruments, and then there's a competition to get those instruments onto the rover. And so after that proposal round, some number of instruments will be selected, and those instruments, the people who developed them and the team of people that work with them will all be included on that rover team. And then just before landing or just before launch, then they usually do another call for proposals. And at that time, any scientists around the world can apply to be part of the team. And they'll usually select around 20 for these missions, 20 to 30 that way. And every one of those scientists and every one of the instrument teams usually brings on a number of students and postdoctoral scholars, and they'll bring on undergrads and graduate students and postdoctoral scholars. And so, as the lead team is the team of people that either built an instrument or got selected for a specific science question, science project that they proposed, and that'll be something like 40 or 50 people. And then the 400 is the teams that work with each of those individuals to make all of those science projects and instruments possible, and calibrate all the instruments and keep track of all the data. And so I started working on missions as an undergrad, and I was first a note taker for the Phoenix mission to Mars. And so I would go to the meetings and take notes on everything that was happening, and that went into the record for the mission. And later I worked on the Spirit and Opportunity rovers as an undergraduate and a graduate student, helping with operations, helping make all those day-to-day decisions. And then thank goodness Curiosity landed, and I got to be a graduate student working on that mission for a long time. And then I was a postdoctoral scholar working on that mission. And now I'm still working with the mission team as a professor.
So Kirsten, how many? We've still got 69 open questions. I have no intention of asking how many. What's your take on this? You want to do another 5 or 10 minutes?
Yeah, that works. Yeah.
Okay.
Thanks everyone for logging in and asking.
Yeah, and again, yeah, same here. I think it's been great, and it's just I just apologize that we're not. I mean, we're actually getting through more questions than we would in person. So Kirsten's doing a bang up job here at keeping this going. And here's a little personal one for you from someone called Carlos. If you had the opportunity, would you go to Mars?
Yeah. You know, I really like traveling, but I also really like eating and people and breathing. And isolation in this form has really been sufficient for me. So I actually prefer to stay on Earth, but I love the robots, and I would love to have people on Mars. So I would love to be able to work with those astronauts and help them as they're selecting samples and bring them back. And I think that could happen. I think that we will be able to do that whenever we, as a society, choose to, whenever we supply the funding and the time and the effort towards that. Now, there are a few major challenges with astronaut health and radiation that will have to be overcome. And I personally am very happy with driving the robots and helping the astronauts and eating tasty food here on Earth.
This is from someone called David. It's not me, but as you talked about Martian meteorites on Earth, could there be Earth meteorites on Mars?
Oh, there could. It is a little bit harder, I think, with solar system dynamics to get an Earth meteorite to Mars, but there could, and that has been hypothesized and discussed as a possible vehicle for life to be transferred to other places in the solar system, which is a real adventure. When we send robots to Mars, they're cleaned, they're sterilized, just like medical instruments, because we don't want to try to find life on Mars and instead find some organism that we brought from Earth. So we want to be really careful about not contaminating Mars with Earth life at this point. Once we send astronauts or something like that, we won't really have a choice, and we'll have to just see if we can keep that restrained to a small part of Mars, and still have other parts of Mars that allow us to explore for those signs of life, which may be really tiny and maybe really tiny parts of the rock or minor components.
So here's another question about perseverance. Mariam Elizondo asks, and I think it's just partly because you didn't have time to do this, but does Perseverance have other functions other than getting the rock cores in case the cores cannot be retrieved for Earth analysis? So what other science is it doing other than just collecting samples and piling them up?
Yeah. In order to collect the samples, we are doing science. So we have scientific instruments on board. We just don't have the like X-ray diffractometer, the thing that zaps the rocks with X-rays and figures out the mineralogy. We don't have the instruments that require drilled samples, but we do have a bunch of cameras. We still have a laser. Actually, this one will have, it's called SuperCam, but it'll have another laser instrument. It'll have the same cameras, and it does have actually a variety of instruments on the end of the arm that will be able to, with higher resolution than ever before, they'll be able to brush off a part of the surface of the rock and kind of analyze the chemistry and mineralogy of a little area as it's sitting on the rock in high resolution. So the one on Curiosity just gets the chemistry of kind of a penny-sized spot, and this one will get a whole grid of pixels showing what the rock is made of. And there's also one other one that's on the mast. It's on here. That's actually going to convert some of the Mars air into oxygen, and that's basically a technique that we can use on Earth, but we're sending an instrument that does that to Mars to make sure that we know how to do that, so that in the future, if we send people, we will have proven some of the tools that enable humans to survive there. One other cool tool, one more that I get excited about, one other cool one that's going up with Perseverance is called the Mars helicopter. And so with this mission, we are sending the first drone to another planet. And that is, it's called the helicopter because the Mars atmosphere is so thin, it has to have these kind of really big blades and be a really small drone. But it will separate from the rover after landing, and then it will fly up in the air and then take some pictures and then land and prove that we can have drones on Mars. And the big advantage to this drone, whether it does much more or not, is that if we prove that we can do it, then in the future, we can really think about all different kinds of Mars missions than we've thought about before. If we could go to Mars and just fly drones and have them hop around on the surface to different areas, it's just a whole different kind of data set that we've never seen.
And then this goes, I mean, I know you talked a little bit about your, how you get involved with the Phoenix lander and all this sort of stuff, but I think this maybe goes a little bit further back. Bridget Noonan is asking, what got you interested in Martian geology?
Yeah. So what got me interested in Martian geology? I kind of followed a different. I was excited by science, but I wasn't committed to a certain type of science. Actually, before that, I really wanted to be an actress, and and then I went to a science high school, and I kind of like learned. I had some really great science teachers, and I thought science was really interesting. And at first, I wanted to do biology, and then I wanted to do chemistry. And then I actually almost came to Rice because I was really interested in material science, and Rice has a great material science department. But I had heard about this program in geology, and I'd heard about it at WashU. Rice obviously now has a geology department, and now has planetary science as well. But I went to WashU because they had this geology program, and it was the first time I had thought that I could solve puzzles, go outside, and do science, and that going outside was part of doing science. And so I got really excited about geology at that point. And solving puzzles on Mars just ended up being my favorite branch of geology. And I got kind of those opportunities to take notes for different missions and see how it worked. And I really love being able to work on a team of people that are all really excited about their work here, and a team of interdisciplinary scientists. So we have to really try really hard to learn to communicate with each other and figure out ways to share our different ideas and forward Mars science. And so some of it I just kind of fell into as I progressed through different ideas of what I wanted to do. For students, I always encourage them to keep trying and try different opportunities, try things that you're not sure if you'll like, because I kind of ended up following different paths and then finding this one, and I love it. I love going outside to do research, and I love being able to ask these questions about why did this get here? Why are there mountains there? Why is there a river there? What's going on? How can we tell how much water was in that river? And ask those kind of questions on Earth and Mars.
And maybe time for a couple more. Fatima Alam asks, why not let Perseverance collect the rocks and bring it back to Earth directly instead of sending different missions? So that's a big picture question now.
So here's NASA's slide about that. Basically, the problem is that if you want to have enough science on that mission to be able to analyze the rocks, like I was saying, it'll also be able to brush off the rock and take really high resolution pictures and do some new science that hasn't been done on Mars. You need this big robot, and that big robot then doesn't want to carry around a whole bunch of fuel that you need to launch back into Mars orbit, let alone the fuel you need to get all the way back to Earth safely. And so that's why you have to have a second step here. So the rover can't carry all of the fuel and everything to somehow get all the way back to Earth. The second mission has to have this base pad and a rover, because it's got to have something with wheels to go collect the samples, which is called cache here, the sample cache. And then it's got to bring them back to the base and actually bring it back to where the fuel is to launch it into orbit. But again, you're not going to be able to land safely and carry that little robot and everything with enough fuel and the full mission design to bring it back to Earth. And instead, you're better off for the mission that comes to get the samples, not landing on Mars. So you only have to do one landing with each mission. It's very hard. We're working on reusable rockets for different things, but this vehicle will not have to land on Mars, but will have to land on Earth again. And so this kind of minimizes, despite it adds complexity in that there's a whole bunch of missions that have to go well, right? Now there's 3 missions that have to be successful, but it minimizes the complexity for each of those missions in a way that enables them to do their job, to do that part the best they can.
So Kirsten, I think I'm going to ask the last question, and there's still 65 more. And there's a lot of science questions and so on, and a kind of, but I think just to follow on with what you said, since you're talking about how NASA thinks about doing missions, and I'm putting a lead into why I'm going to ask Michael's question, but obviously part of this is we're hoping to send humans to Mars sometime in the next couple of decades or so. And so this is a kind of science question, but related to that, which is, again, this is from Michael. If the atmosphere won't allow the water to become a liquid, how can we live on Mars? And then he says, do we have to suck ice chips to get water? But how can we, if you can't have liquid water on Mars, how can we live on Mars? How can we get people on Mars that can live there?
It's a great question, and it's definitely one, again, I do want to do one more plug for if you're a student and you're listening to this, we need a lot of new ideas for this, right? We're working, undergraduate students, graduate students are working on this right now, on working on like different parts of this problem, because living on Mars is a complicated problem. If you really want to have a colony of humans on Mars, they are going to need to have habitats that provide, that contain their own atmosphere. And in that atmosphere, you can make that atmosphere denser so that you can breathe it and so that you can have liquid water. You can't survive in the Mars atmosphere as it is today. And trying to make the Mars atmosphere thick like Earth's would you would need about a millennium, right? So you need something like 1,000 years and different tools, and it would actually be kind of it's not sustainable at this point on Mars. So instead, you have to have enclosed habitats. You want to protect your people from radiation from space because there's no magnetic field. There's a lot of radiation even at the surface of Mars, so you may have to put them underground, maybe in a lava tube or a cave. So you'll have to have enclosed habitats, protect them from radiation, but we will have to find a bunch of creative solutions for like the plants that they'll grow, the way that habitat will work. Will you send a mission before that's a builder mission and it builds the entire kind of colony and then people come later? Will you have to keep bringing food from Earth, or can you find ways to grow food on Mars? What kind of spacesuits will they wear that will enable them to get the resources they need outside, bring them into the safe enclosed place? There's just tons of questions about how that will really work. And a lot of them we don't know yet. We've got to keep investigating, and we've got to keep having some of our engineers and our bright minds of today and of the future work those questions out. You probably will have to get some ice from the poles, or you'll have to learn how to get, you probably won't, it'll be hard to get enough water from just the air. We'll want to use as many resources as we can from the Martian surface itself. But yeah, there's a lot of questions to be solved there.
So thank you, Kirsten. I mean, normally we get through maybe 5 or 6 questions, and just so you know, for those of you who I'm going to apologize to in a second, Kirsten has just answered 30 questions. So I think that was a Herculean effort, both fantastic talk, and I hope from the answers to the questions that you actually see not just how passionate she is about this, but how exciting this work is and how much we're learning, not just about Mars, but about Earth. And again, I apologize for all of you who are asking lots and lots of great questions. But this has been a great format. I think I've actually enjoyed it, sometimes more so than the in-person ones. And I hope you'll join us again. I think we might try and do more of these, but certainly back on campus when we're there. And we will be posting the recording of this, maybe just the talk. I'm not sure about all the questions and answer part, but we will post it on the Rice Space Institute website, which is RSI for Rice Space Institute.rice.edu. And we'll be sending out using, I'm sure Kirsten will post it on her social media connections too when we get it. But I think this has been absolutely fantastic. And again, I apologize if you didn't get your question answered. But Kirsten, thank you very much. This was fantastic. And I think our experiment worked pretty well. So I appreciate it. And everyone, again, stay safe, be good, and stock up. And Kirsten, thanks a lot.
Wonderful. Thanks so much for tuning in. Thanks.
Thank you, everyone. All right, Kirsten, I'm switching everyone off. Are you good with that?
Yep.
All right, thanks all.